This is Mrs. O'Neill for AP Chemistry, Chapter 8, Section 7, Exceptions to the Octet Rule. And that's what the Octet Rule is, just a rule. It's just a guideline. It's not a law. So that's one of the objectives to understand in this section. The other objective is to understand that the exceptions include odd number of electrons in a molecule and the fact that some elements actually can obtain more than an octet of electrons, and that's also the other exception. So I suggest to pause, write down the blanks, the words in the blanks, and then play to hear my explanations. I also suggest writing out the molecules, writing out the structures, and doing the examples. So here we have odd number of valence electrons for nitrogen monoxide and nitrogen dioxide. So nitrogen monoxide has two possibilities. You might want to pause and see if you can come up with those two. Here they are. We have a double bond between the N and the O, and the difference here is that one lone electron can either be on the nitrogen or it could be on the oxygen. Again, I suggest pausing the video, see if you can come up with the formal charges on both of those nitrogens and oxygens in those molecules as a review. I came up with the first molecule, both nitrogen and oxygens are zeros, but in the second molecule we have a -1 and a +1. So obviously then the best molecule would be the NO, the very first one, where that single electron is with the nitrogen. So we have to go by formal charges. That's why it was important to figure that out last section. So here's nitrogen dioxide. I've already given you all three possibilities. So we have oxygen 1 on the left, which is singly bonded. We have oxygen 2 on the right, which is doubly bonded. But it's that lone electron again. So is the lone electron better on the nitrogen in the middle, the right side oxygen with the double bond, or the left side oxygen with the single bond? Again, pause, come up with the three formal charges, and I get this. So I get that the last one has all elements, the nitrogen and the two oxygens, being 0. So of course that would be the best possibility. That's probably the molecule that's going to exist the most. The other exception is less than an octet. Beryllium and boron, they do not have to have an octet. They're happy with beryllium bonding only twice and boron bonding 3 times, which should kind of make sense. Beryllium is in group 2 and boron is in group 13. So beryllium has 2 valence electrons and boron has 3 valence electrons. So it should kind of make sense that they don't need that octet. So if we look at boron trichloride, we have boron in the middle because that is the most, I should say the least electronegative. We count up the valence electrons we have, we put all the dots around it, and voila, when we count them up, we have all 24 electrons used, and boron is happy just with those 3 bonds. And if we are to look even deeper, we would do the formal charges, let's say, of boron trifluoride. And we would find that, again, the 3 single bonds with boron and fluoride all have a 0 formal charge. But if we look at something like this and we would include a double bond to make boron have 4 bonds or 8 valence electrons, we would see that there's a positive-negative formal charges going on there. How about our third exception of more than an octet? Elements in the third row, the third period, and that they are usually larger elements, they tend to exceed the octet rule, and that's because of their polarizability. And that's going to be a word that we're going to discuss and talk about in the future, and that's a word that AP Chemistry readers, they really like this word polarizability. And it just means that the bigger the atom, the bigger the molecule, the more complex it is, means the more polarizable it could be. The more electrons can kind of be around there and become more polarizable. So here's another example of phosphoric acid. Again, we look at the phosphorus in the middle. Instead of the 4 normal bonds, it has 3 single and a double, making 5 bonds. So phosphorus is another one. He's a bigger atom, so he is more polarizable, and he can have more than that octet rule, more than 8 valence electrons or more than 4 bonds. So if we do come up with these extra electrons and there's nowhere to have a bond, where would we put these extra maybe lone pairs of electrons? Well, if you were to draw bromine 1, 2, 3, 4, 5, pentafluoride, bromine pentafluoride, we would end up having 2 lone pairs of electrons somewhere to go, and we would just put them, boop, we would put them right in the middle. Okay, and this again is going to make you understand the geometries and the polarities of some of these molecules. See you soon.